Hi folks, so the questions we have in front of us here today are the 2017 Section A Ordinary Level questions from the DCG paper. As always, it's 4 questions on the page. These are 4 the short answer questions and you have to do 3 of them. What we're going to do in today's video is working through all 4 of them from A1, A2 onto A4 as well, okay? So I'm going to zoom in here on this one, starting with a perspective question here on A1. Okay. So for question A1, it says the image below shows 3 steps at the entrance to a home. The drawing on the right shows the plan and a partially completed perspective view of similar steps. Complete the perspective drawing of the steps. Okay, so you can see here they've kind of given us a real life image of the steps, and what they have here over here is the plan view of the steps. They've set up our picture plane, they've set up our ground line, and they've set up our horizon line with our 2 vanishing points VP1 and VP2 on it. And obviously then you can see here that they have the partially completed step figure done, and all we have to do is complete the rest of it. Okay, so what we need to know about perspectives is the direction of the faces, okay, in the case of the steps here. So if you think of this face here of the steps, which will be seen as this line in my plan view, the direction of the faces dictates where the points have to go to and which vanishing points. So if a face is going in this direction, the same direction as my pen, that is parallel with this line here going from my spectator to pitch plane, it's going to go to VP2. So any faces that are going in this direction are going to go to VP2. Any faces that are going in this direction are going to go to VP1. Okay, so what we're going to do now is, this one isn't actually too tricky. It's a case we want to build it up slowly. So like this face was completed here, we want to complete this face as well. So from this point right here, okay, from that point right there, I would like to vanish it to VP2. So extend that out, and to make my life then a little bit easier, it's about a bit of sliding set squares, because I know at this point right here it's just going to extend up vertically. And as we can see there, then it's a case of heavying in the important information. So that's the first step completed. Excuse me. So now at this point right here, which is technically this point here in my plan view, now what I want to do is I want to complete the next portion of the step. Okay, so the next surface step, like the bottom step was here, I'm going to complete the next surface. So where the next step starts is technically here. You can see it was dropped down already. Okay, where this point comes to the spectator, but where it hits the pitch plane, extend it down. Okay, and what I'm going to do is extend that point to VP2. Likewise with this one. And to make our life a little bit easier then, at this point right here, which is the starting of the second step, I know it's going in that direction, that edge there. So this one is going to extend out to VP1. And what we can actually see there, to make our life a little bit easier then, is I can actually see the edge of where it is heavy as far as right there. That's where they're meeting. So these questions are kind of nice questions to get. And at that point there, likewise where here it extended up vertically. So I'm going to draw on the step as well. And there we have it. So that's the next step done. Now the last part is, you can see the back edge here is already extended across to our vanishing point 2. At this point here, which is this one, the edge here is going in this direction. That's this direction, so it's going to go to VP1. And then it's simply a case of heavying in what's needed. So there we have it. That there, guys, is question A1 completed. Now you could check your accuracy and so forth by extending down points. Okay, just to show you here, let's say I wanted to find this back corner here, which should match up there. Technically that should meet my spectator right there. So if I was to extend that down, then depending on your accuracy, okay, especially with these drawings since they're so small, I'm using a pen at the end of the day. So right, slipped a little bit there, about there, and as you can see, that's working out pretty good. Okay, it's giving me where the back corner is, so I know I'm quite accurate. Now you don't actually have to do that. If you do that and you're actually not accurate, then you're just giving the examiner a chance to obviously maybe take a mark or two off you for your accuracy, okay? But what you've shown here is that you're vanishing to the right vanishing points, thereby determining the correct faces, okay? So that's question A1 completed. What we're going to do now is to question A2, which is at the bottom of the page. Alright. So for question A2, it says, glamping or glamorous camping appeals to those seeking adventure while on holiday. The graphic below shows an image of a glamping hut which is based on two semi-parabolas. Okay, so two half parabolas is what they're saying here, semi-parabola like a semicircle. In the given drawing, a portion of one parabola is inscribed in the rectangle VABC. Okay, so you can see it here. Its vertex is located at V. Part A, locate the remaining points on the semi-parabola in the rectangle VABC and complete this curve. And then part B, the second semi-parabola is in rectangle V1. Okay, so that's the other vertex, DBC. Okay, is a mirror image of the first parabola with BC as the axis of symmetry. Draw the second parabola. Okay, so what we have to do is we have to complete the parabola on this half of it here. And anytime we're drawing a parabola inside of a rectangle, what we're going to do is we're going to divide it up into equal number of sides. So the side AB is going to be divided up into the same amount as the side AV. Okay, and you can see here they've already kind of given us the portion of the sides here that we have to divide it up. So I can actually just take one of them, try and be as accurate as possible. So I'll take that distance and I'm going to step it out how many times whatever I'm left with. So and this will actually determine how much I have to divide the opposite side into. So I'd say it's actually going to be 1, 2, 3, 4, 5, about 6 I'd say by the looks of it. So as you can see there, if I was to number these, where A is, let's say 0, this is 1, 2, 3, 4, 5, finally into 6. Okay, as I number them, so you can see I have six sections. Section between 0 and 1 is 1, 2, 3, 4, 5, 6. So likewise with AV, now I have to divide that into 6 equal parts. So to do that, first of all, I might be able to do it by maths. So I'll check the measurement. And it's working out to be 83, just under 83 is divided by 6. So that doesn't really go. So just thinking, does 83 go? 60, 84, no it doesn't. Okay, so in that case what I'm actually going to do is the method that you would have learnt in first year technical drawing called division of lines. So in the space here opposite, I'm going to extend out a line, doesn't matter what angle, and I'm going to do 6 equal measurements. Okay, if I needed 5 I do 5, so I'm going to do 6 equal measurements of 10. So mark back 10, 20, 30, 40, 50, and finally 60. At the last one, I'm going to connect that to A. And what I'm going to do then is, using sliding set squares, this helps me determine how I divide a line up into 6 equal parts when I can't use simple maths. Okay, so now what we're going to do is we are going to locate our sections. So at each one of these points going up and down here, I'm going to extend across a line horizontally. Okay, and this is going to help me determine my points. So if I was to label this, how would I put it, 0, 1, so I'm going to go here with my 0, so that's 1, 2, 3, 4, 5, 6 onto 0. Okay, so you can see here where 1 connects to the vertex but goes through the one horizontal line, that gives me a point. Likewise with 2, where 2 goes to the vertex but where it goes through the 2 horizontal line. Same method follows. So for 3, I'm going to connect that to my vertex, and that will give me a point on the 3 horizontal. And I continue the same process then for 4 and 5. that gives me a point on the fourth one and on the fifth one, and then finally there is also a point here, right here at B, which is the sixth one. So it's a case then of sketching in my parabola, I should say semi-parabola. Okay, so there we have the semi-parabola, and that is part A completed. Now what I want to do is part B, where it said it is a mirror image, okay, with BC is, so let's draw the second parabola. Second semi-parabola in rectangle is a mirror image. So I can actually use the line BC as an axis line here, and I can just mirror the points over. So I know there's a point right here, and I know there's a point here, but I have to find this one, this one, this one, this one, and this one. So just to find them, I'm going to extend them across horizontally as far as I think I need them. Up to there, up to here, up to here. So using my compass, I'll take the distance from the axis line to the relevant points and mark them. So there we have it, there's our various points. So likewise, once again, sketching our curve. Okay, there we have it. That there is part B completed, where we just mirrored the points about our axis line here to get the parabola, the exact image of it on the opposite side. So it's like taking this and flipping it over by using this axis line. Okay. First part then was where we split up our rectangle VABC into the relevant number of sections depending on how many you were kind of given at the start to determine it. Okay. So that's question A2 done. What we're going to move now onto is question A3 at the top right of the page. Alright. So for question A3, it says the 3D graphic below shows an image of the Tom Clark Bridge in Dublin. The bridge was constructed in 1984. The bridge can be raised as shown in the graphic to enable large boats to sail further up the River Liffey. And then the elevation of the bridge is shown on the right in its closed position. The bridge is rotated upwards through an angle of 60 degrees about point P until point A reaches the line AA1. And then draw the bridge in the open position. So you can see here obviously the bridge, okay, the Tom Clark Bridge up in Dublin when it is in its kind of rotated position to let larger boats sail underneath it, okay. And what they've done is they've given us a graphic of it here, and they've shown us the bridge, okay, so we can see here, this is obviously like the little structure that it's kind of up against to give it support, and this is its kind of hinge point or pivot point. And we can see basically that this is the kind of blue part here is the bridge, okay. And what we have to do is it's rotating up at 60 degrees, and we have to move this section of the bridge up until it's in this position, okay. So they've given us A, and they've rotated it up until it's in this new position called A1, okay. So if we wanted, you could use labels. So if I wanted to call this, let's say this point here is B, don't have to use that one because it's on the same line, so I'm just going to call that B. Okay, you don't have to use labels, but I find them helpful. Let's say this point here is C, D, and then finally here to E, which is right in there, as you can see it. So I'm going to put it in here. So technically E, you can see, has already been rotated around. So I'm going to call that one E1. And I'm going to put in this heavy already from E1 to A1. Because I know that's in its correct position. And now what I've essentially to do is I have to rotate B around until it's in its new position. Okay, so there's a couple of ways you could do this. Starting off with point B. Okay, I'm going to take my compass point, put it on P, which is the pivot point, and put my mark point or my pencil point, in this case my borrow point, on B, and I'm going to rotate it until it's in its new position up there somewhere. Now there's a couple of ways, as I said, you could do it. I could connect P to B by doing a straight line, and then using a protractor I could measure 60 degrees. Okay, so I'll just show you that one there first. So from P to B, I could do this one like that, and then using a protractor, which I'll just grab here now. Using a protractor, I could measure with my point on P 60 degrees like that there, and then by connecting a line would mark it right there like that, and that will actually give me the position of B. Okay, and that's one way I could do it. Now probably the easier way of doing it though would be to take the distance from A to B, because that's a true length, like that distance right there from A to B. Just make sure I have it exactly. And because I do have the position of A, now this should go through right here. And you can see it does. Okay, happy with that. Probably a tiny bit out. Okay, I am using a biro at the end of the day, but that position there is showing me where B1 is. So now I can connect those. Okay, so now I've got the position of B1. Now at this point I know B connects to C. So likewise I'm going to rotate that. So from P to C. Okay, so C is somewhere down along here. Likewise the same happens with D. So I'm going to rotate D about. Okay, so D is somewhere out along that rotated arc, and then C is somewhere out along here. Now, what I should note also is, I also already have E1, and E connects to D. And what's important to note is the relationship between them is that they're actually, the line AE and the line ED are perpendicular to one another. We can see that here. So it's very simple to find, rather than measuring 60 degrees or anything like that, I could, just using the geometry that's available to me, I could connect the line A1, E1 technically here now, and then with my set square on that, I'm going to pivot it about to create a perpendicular angle. Now that I've got my perpendicular angle, from E1, I'm going to do a line to cut into the arc D, which will actually show me the position of D1. And now I can heavy that. Okay, so that's quite helpful there. Now the next part is, I know D connects to C, which also connects to B. Now I'm going to note the relationship from A to E is parallel from B to C. So BC is parallel to AE. I've already got A1, E1, so therefore B1, C1 should also be parallel. And because I have the position of B, I can just do a bit of sliding set squares here until that cuts through the arc C. And I can see it's cutting through right there. So that's going to be my C1. So heavy in that. And then I can connect C1 to D1 like that there. Okay, so that was probably the quickest way, is just understanding the geometries and looking for what was around you. The very start you saw here, I connected P to B using my protractor. I measured an angle of 60 degrees. The other way I could have done it was I took the true length from A to B and I marked from A1 down to cut it. Okay, that's probably the quicker way than using a protractor. And then understanding the relationships between lines and then perpendicular and parallel lines. Okay, so now there guys, we have rotated the bridge until it's in its rotated position, or a rotated angle of 60 degrees. So that's question A3 done. What we're going to move on to now is question A4 at the bottom of the page. Alright. So for question A4, it says, a desk tidy in the form of geometrical objects which are in mutual contact is shown in the 3D graphic below. The solids rest on a rectangular base. The drawing on the right shows the elevation and partially completed plan of the desk tidy. It consists of a cylinder. Okay, so we can see the yellow cylinder here on the outside, which is obviously dictated by the letter C here. It consists of a cylinder, a sphere and a cone. Okay, so we've obviously got our sphere here that's actually been cut at the top of it, sphere A, and then we've got a cone here okay, cone B, and we can see it's actually been truncated, which basically means the top of it has kind of been cut off, or in this case it's actually the bottom of it because it's upside down, so an inverted cone. The sphere and cone have been truncated as shown, so that's what I was saying there, so they've been cut. Okay. Part A, draw the plan of the truncated cone B. So what we have to do is we have to draw the plan of cone B down here. Okay. So, and then part B, draw the plan of cylinder C in its correct position down here as well. Okay, so this is actually solids in contact. And what we have to note is that we have sphere A in its elevation, and we also have it in the plan view. And you can see here they've left us a little gap here. That's because our cone, you can actually see in our elevation, because when we look down on top of it, our cone is going to slightly overlap over the edge of the sphere. Okay, so they've left us that little gap there because we're going to have to put in a bit of hidden detail for our sphere. So what I'm actually going to do is the center point. Okay, when I look down on top of that cone, the truncated cone in this case, I'm going to still see a circle. So I'm going to extend down the center point because I know it's out there, and then I also know that the cone is touching on what would be known as the extreme generator. Okay, in this case it would be the extreme arc of our sphere, and that arc there, or I should say the circumference, would be seen as this axis line here. So that point of contact is actually, if I was to find, you can see it here, they've shown us where the point of contact is. If I was to find that down here, that technically is where the point of contact is, right there. And where the point of contact is, somewhere has to be the center. So if I was to extend out this axis line like that, that there is the center of my truncated cone B. So I'm going to just heavy that in now. So I'm going to take the radius from up here. That will be my radius right there. I'll take that, I'm going to draw it in. And then I can actually complete this portion. I'll put in the hidden detail. Of cone A, of sphere A, I should say. Now, when I'm looking down inside it, you can see here they've shown you where the sphere has been truncated. So we're kind of seeing obviously a circle there. If I was to project down this point right here, I would actually see another circle, a really small circle on the inside that would have this radius. Now, as you can see with my with my compass that I have, it actually doesn't reach into that. So I'm just going to sketch that in as best I can. This is technically cheating here, but just to represent it as best I can. So what that would actually look like is maybe something like that there. Okay, so there we have cone B. Put it in red as well. We've got cone B in its correct position in our plan view, so that's part A done. And part B then, it says draw the plan of cylinder C. So we can see here cylinder C is slightly in front of sphere B. Okay, it's just been rotated around until it's slightly in front of it. And likewise, we can locate the plan view of that by simply, first of all, finding the center in the plan. And I know my center has to be somewhere down along that line for sphere C, for cylinder C, because cylinder, when I look down top of it, is going to give me a circle as well. And somewhere down along that line there is going to be the center of it. But what I need to do first of all is I want to draw that cylinder in such a way that it's in contact, like we had over here with our cone, where it was on the extreme, I suppose, arc of the sphere A. So same thing, I want to move this cylinder, just take it until it's in a position that it's in contact right at the side here. Because any cylinder touching a sphere will always meet that sphere along its axis and the center line here. Okay, a cylinder will always meet it. So what I'm actually going to do is draw that semi-cylinder, or sorry, not semi-cylinder, that cylinder in right there. So that's like I've taken this edge here and I've rotated it around A. So in this position it's rotating back here. So this is the position of it where it's meant to be. We just have to find the exact center. But I'm going to take that there and I'm going to rotate it around. Nice and easy. And what I'm essentially going to do is find that ghost cylinder, which is generally what we call it. So just set up my compass here. So I'm going to take this radius here, right there, and what I'm going to do is from the center, or from the axis, I'm going to mark that out there. And that technically, if I was to do it again and draw that in ever so lightly, just a little bit here. What I've essentially done here is this cylinder C, I've moved it over here. Okay, but what's really important is where the center is, and this center point is when it is touching on the extreme generator. So if I was to take that center point down, okay, where it is located in my plan, and then rotate it about, I'm going to rotate that because everything would rotate about the sphere, okay, and the center point of the sphere is there. Where that distance, which is my radius, okay, of my cylinder, when it has been moved into its correct position now here, okay, where that distance has moved out and rotated around, I have now found my center point. And having now found the center point, I can now draw in my cylinder. So this one takes a little bit of visualization. So I'll take the radius from here again. And I should be able to also connect center and the center, which technically would give me a point of contact right there. That radius should be the same, and that seems to be working out just fine. Just takes a little bit of finesse now in drawing this. Okay, so now we have our cylinder C in its correct position in our plan view. And as we can see, the center is located down here, and it was simply a case of getting this radius and adding it out here and then rotating it around. I added it up here, brought it down, rotated it around until it was in its correct position. As always with solids in contact, you generally should, they haven't asked us for it here, but I would always show my points of contact. So the one for the sphere and the truncated cone was given to us, which was here, and then we found it here in our plan. And to find them for the sphere and the cylinder, our points of contact is where the two centers connect together. So that there, right there, is a point of contact. And I'd usually write POC beside it. And then if I wanted to find that in my elevation, it's simply a case of projecting where it is in plan up to my elevation. And I said previously where a cylinder meets a sphere is always going to be along the sphere's center point or center axis line. So that's where the point of contact is going to meet it, right there. Okay, so that is question A4 done, guys. That one was based off of the solids in contact topic. Hope you found those 4 questions helpful. That was the 2017 ordinary level section A complete. Alright.